Hello, my name is Lauren Butling, and I'm going to be teaching you about thermodynamics. I would like to begin this lesson with Newton's 3 laws of thermodynamics. The first law, also known as the law of the conservation of energy, states that energy cannot be created or destroyed, it can only be transferred from one kind to another. The change in internal energy of a system is equal to the heat added to the system minus the work done by the system. A light bulb transforms electrical energy into heat and light energy. The second law says that when various reactions happen in the body, the entropy either increases or stays the same. Entropy is the measure of disorder in the system. This law is a lot like cleaning your room, because whenever you clean your room, it always has the tendency to become messy again. The third law states that when the temperature reaches absolute zero, the entropy of a system approaches a constant value. The entropy is determined by the amount of ground states. When the substance is pure, it is at absolute zero. When the movement decreases, then the entropy movement decreases as well. Now I'm going to discuss Gibbs free energy and spontaneity. Gibbs free energy is the amount of energy available to do work. When a reaction is spontaneous, or exergonic, the reaction releases energy and Gibbs free energy is negative. An example of this is the metabolism when it releases fuel to our bodies. When a reaction is non-spontaneous, or endergonic, it absorbs energy and the Gibbs free energy is positive. The equation for Gibbs free energy is available energy equals the total energy changed minus the temperature times the energy lost to entropy. Cells are continuously recycling products into other reactions. An anabolic process is when smaller molecules make a complex molecule through non-spontaneous reactions. A catabolic process is when sugars are broken down, giving off energy, making it a spontaneous reaction. These two processes work together within the human's metabolism. Now I'd like to discuss the energy needed to get a reaction going, regardless of whether it's spontaneous or non-spontaneous. This kickstart energy is called activation energy. This energy puts the molecules at a transition state and is usually in the form of heat energy. Shown on an energy versus time graph, spontaneous reactants have a higher energy than the products, and non-spontaneous have the opposite. Activation energy speeds up molecules, causing them to glide more frequently with more force. It's like putting 100 kids in a 50 by 50 foot bouncy house. The atoms and molecules move, enabling them to reach the transition state. Adding heat to a system will also cause these molecules and atoms to react more often. Next, I would like to discuss ATP, otherwise known as adenosine triphosphate. ATP is a unit of molecular energy that energy transfers within cells. It stores the energy we need to do just about everything we do. It is present in the cytoplasm and nucleoplasm of every cell and powers muscle contractions. The creation of ATP is a non-spontaneous reaction, and the breakdown of ATP is a spontaneous reaction. In phosphorylation, phosphate groups are added to a compound requiring energy and therefore is non-spontaneous. On the other hand, dephosphorylation is when phosphate groups are removed from the ATP, releasing energy and therefore is spontaneous. In hydrolysis, water is added to the reaction, separating a bond in a molecule using water. And this energy is released, making it favorable. In dehydration, water is released to create a more complex molecule, needing more energy, which is unfavorable. In coupling, however, two reactions are formed to form one favorable reaction, therefore releasing energy. This energy coupling leads to metabolic disequilibrium, meaning the cell's spontaneous reactions power the non-spontaneous reactions. However, in metabolic equilibrium, Gibbs free energy of a cell reaches zero, so it can't do work. And hydrolysis provides enough energy for the cell to use because the catabolic processes fuel the anabolic processes. Almost all of the functions humans perform use energy. Not all energy is used, however, and the energy is released in the form of heat. When the heat is released, so is entropy, and entropy needs to be released from our bodies. Now, I'm sure you're all wondering, wow, how does food even give us energy? Well, foods provide a variety of nutrients, but all food supplies us with energy. Catabolism breaks down the food as soon as it enters our mouths. Our saliva breaks it down even further and sends it through our intestines and our bloodstream. The bloodstream spreads the food into cells all over our body. The mitochondria, or factory for the ATP in our cells, provide power for the cells. With energy ATP stores, the body takes those broken down nutrients and then rebuilds them through anabolism. The constant flow of materials keeps the metabolic pathways from reaching equilibrium. The cells can't maintain equilibrium because they are open systems, and open systems continue to bring in and push out materials in cells, allowing the cell to work throughout its life. Thank you so much for watching, and I hope you learned a little bit about thermodynamics.